Hi, welcome to the part 4 of transistor scaling. I was not expecting that I would go to part 4 for transistor scaling. I was thinking of wrapping it up in a couple of parts, but I haven't even fully covered 500 to 130 nanometer, and it's already part 4. But anyway, I think things will get a little bit quicker after this. I wanted to make sure that I spend enough time on the required topics, um, and don't rush through things. So, I mean, you might be thinking that you don't need to know all the scaling things in order to be a good circuit designer or design engineer like myself, right? To some extent, it's right. Even if you don't know the scaling journey and all that, you can still do a pretty good job in RTL design, validation, physical design, and overall RC design. Um, but understanding some of these things, um, understanding, for example, if you want to go to the latest technology and start understanding it, everything has a background. Things have come in decades where things have progressed to where they are right now. So it's always good to go back and understand in every process technology how things evolve. The smallest transistor that we have today, how we came down to that. It didn't happen in a couple of years. All this started a long time ago, and it evolved, it slowly changed, things happened gradually. Um, every 2 years, transistor got smaller, and a lot of things went into that. So I think if you understand some of the thing, every time a process technology gets smaller, it has impact on delay, it has impact on power, it has impact on density, it has impact on design rule constraints, it has impact on routability, placement, so many things. So understanding some of the things really help you. It make you a better designer. And you don't need to know every little details behind, but most of the major things or important things you need to understand, you need to know the intuition behind those. That's really the key thing here. Um, all right, so last video was about short channel effects. So in this video, I'm going to look at from 500 nanometer down to 130 nanometer. What were some of the things that were done beside scaling the length in order to make the transistor a good switch? And these things actually continued beyond 130 nanometer. There are other things we had to do in order to make the transistor work in a way we want, but these things also continued. So I divide these into three main categories. One is oxide scaling, silicon dioxide, I mean, the one between gate and the channel. Then engineering of the source or and drain regions. Then the well, between N and P there's a well, which is where eventually a channel is formed. So engineering of that. So goal overall is to combat against the short channel effects. Short channels, when they are too small, it's very hard to improve the current. So the on current amount needs to keep increasing, the off current needs to decrease, and we need to stabilize the voltage threshold. We control the voltage threshold, not the shorting of the channel. All right, so that's where things change in these three areas. Okay, so the very first one, oxide scaling. So oxide, the silicon dioxide is here. Every time this length got smaller, this thickness of the oxide had to get smaller. over the generation, it was seen that the oxide thickness roughly was made smaller with this factor of 0.5. So length you divide by 45, that was really the thickness in the oxide. And that was really done, if you look at when you reduce the thickness, what really changes? This is a capacitor, right? There's a positive charge and negative charge happens here. You reduce the distance between the two in a like a parallel plate capacitor. What happens? Your capacitance goes up. Sorry, so your capacitance goes down. Okay, when your capacitance goes down because this thing got smaller, your influence here is more. Okay, you're really controlling this area more with this voltage. And that's really we want. We want to control this gate in an ideal way that when the voltage is one type, it's off, and another type, it's on. That's the ideal. We don't want this controlled all by this one. We want to control this one, and in order to make more influence, you really have more control here when the distance gets smaller. Okay. Another way is you also look at it by reducing this depth. You are also controlling the channel depth here. Think of that as pretty common sense that if you have electrons here flowing here, the less control of the gate will have. The more control will have if they really flow at the top. Then we will drag them in, and through supplying some voltage, we will move them here. So as you reduce this thickness, actually the channel depth got also reduced, and that's also something we want. So in order to have a better control, oxide scaling is super important. Second thing is, okay, we managed to have a better control here through this by reducing this one. The key thing here is these regions, before I never do this, I mean I've shown you an example, but they used to be like this over here, not this shape. The short channel effects, if you remember what I mentioned, that this voltage now for this short channel becomes so critical that it literally drags these electrons here. And that happens because we were having a bigger area. So let me draw this. So we have this much area, this much power into the channel here. Now one way is if you reduce the area that is facing the channel. I mean, the channel is supposed to be with reduced thickness, we can reduce the channel depth, and it will be here. So the area we actually face, it might be even less than that, but this is just a picture I drew. The area, the charge actually that we are showing to the channel here is actually reduced. So, and then you can't have that reduced thing all over the place here, because you need a lot of supply of electrons here to go from here to here and also here. That's one thing. And more supply of electrons mean more current, so faster it is. And also if you make it smaller, there will be, it's the same thing. Resistance, what happens? If the area is smaller, resistance is more. So by keeping here and making it smaller here, you're actually, the main thing was that we want to have a smaller charge, smaller electric field here. We are kind of doing that, and at the same time we're making sure, because you want to increase the current here, but you don't want to have a decrease here. There's no point then shrinking if you can't flow the electron properly here. So you need like a deeper area. So two things were done here, as one I already mentioned. I believe this one I didn't say. So not only we make this extension, this is called source drain extension. It's made on both sides equally, similar way. It's called SDE. This area is also made lightly doped. I mean, this is N plus, right? N plus means there are electrons are in the majority carrier. So if the doping, I mean, pure silicon was not, electron was not mobile. So in order to make more electrons, in order to make it more conductive, we added impurities, and the result of impurities is that we have more electrons. So you put less impurities here compared to here. And that's why we had these spacers in order to grow this area until here. So this shape plus low, lightly doped. Now two things are very important. This overlap with the gate, so gate is here, right? And this area actually starts here. So there is this gap, overlap. Similarly, this is the overlap between gate. Gate is here. These were the spaces, by the way. Gate is only until here. So this overlap that I'm showing here and this depth of this, both of these are important. I mentioned here that the overlap about 15 to 20 nanometer. This overlap helps because it kind of creates a depletion region underneath the gate. Okay. Keep in mind that this is N, this area is P. So when it's connected in a way, this whole junction is reverse biased. So moving this underneath helps in some way to create this depletion region. Remember how this channel conducts? Initially, when you apply a positive voltage here, it pushes all the holes away. So in this region, we create a depletion region. I mean, it doesn't have anything. And then a little bit more voltage apply here. All the electrons come from here and drag from here, and they create an inversion here. So this overlap kind of helps building that depletion region and inversion. But if it's too much here, that's also not good because it's kind of pinching off the channel. So I think they found that 15 to 20 nanometer overlap was a good one. Then this depth 30 to 40 nanometer was a good one because if you reduce, I mean reducing is better, right? Because we would reduce the area facing. And I already mentioned if you reduce this further, you will create a problem. You will create a high resistance. Too small is not good. It kind of blocks the current flow. So they found that 30 to 40 nanometer here is good. So that's about source and drain, kind of similar things happen. STE is important. This also called lightly doped. Sometimes the term used for lightly doped is LDD. Lightly doped drain, even though it's here same, but it's called drain. So those two things I used. By the way, a very good explanation, especially these numbers, is mentioned in, and that's where I took these numbers, is Intel Technology Journal in 1998. They explain these things pretty well. The final thing is channel engineering. So two things here. One is that now we talk about this, and now we're talking about this area. This is a P, this is for NMOS, this is P plus. Two things that happen, which I'm showing here in two different colors. One is this yellow thing. This yellow thing means, actually, one this yellow thing and the other one this greenish thing here. These are the two factors. The yellow thing I'm going to explain is called super steep retrograde valves. Yeah, a tricky name, but it's not that complicated. Yeah, I'll show you. And the other one is the halo implants. Sorry, not cells, halo implants. Okay, what are these two? So I explain on this side retrograde wells, his side halos wells. Okay, so let me explain for first of all this factor, retrograde wells. So as I said, not super complicated, and just try to understand the basic things there, the basic intuition, I mean. So what we do is, sorry, I'm keep going back and forth. They found out, I mean, researchers, okay, as they were shrinking the transistor, that the problem here is in this region. Before we had a uniform concentration of doping, right? This is a P plus area. Means impurities were added to silicon in order to make more hole carriers and less electron carriers. Because we don't want current flow here, and this is we want to make P plus because it's P, this is N, this is a reverse bias, so it's a blocking thing here. Ideally, electrons are pulled here, a channel is created here. This is why we made this P plus. So if generally the concentration of holes is everywhere, that was the previous case. But if you make this the profile of doping in such a way that in the top region, I mean eventually here there will be a channel, right? But kind of in the top region, in this region, maybe I should have put this yellow here too. Your concentration of impurities is less, and as you go down deeper in the bulk area, the concentration of impurities is more, and that helps the current flow here. So you were probably wondering why is that the case. Remember this. I think I put this equation before. No need to get scared from this equation. All this equation is saying that the velocity of electrons is proportional to the electric field. And I mentioned this thing at that time, mobility. Mobility is how easy electrons can move within a material. Like the crystal structure. How is the crystal structure here? Because as I said, okay, you have extra electrons, or sorry, here you will have holes, a place where electrons can move. Okay, in the crystal structures, how when you have more concentration of holes, how is current going to flow through that? It turns out, remember this thing, this mobility, the more concentration it is, the less mobility it is. Think again, what did I say? The more concentration of doping, the harder it is for the carriers to move. And why is that? Because carriers now start moving, then hitting each other. Scattering effect, I mentioned that. It's too many, it's a problem. They hit each other and that slows down. So you're probably thinking there are more holes now, but actually the flow may not be that good. So just remember this one. Because of that, they said, okay, in the area where we want a good electron flow, good mobility, make the concentration low. In the areas where we don't want any flow, have a higher concentration. You want a higher concentration because you really want more reverse bias this area. You don't want any electron here. You want to have high resistance in this area. Okay, exactly. And the other thing they did, so that is called retrograde. Retro backward side is a low profile, it's a high profile. That's all it is. It has a fancy name, but under the hood, the concept is pretty simple. The other thing is, here is another fact. The depletion, so if this is a reverse bias, right? This was a N, this is P for NMOS case. And you apply a higher voltage here, a lower voltage here. So then this junction gets reverse bias, which is good. We want it to be reverse bias, but we don't want current flow here. That's a problematic current. The current that we want is right underneath gate. And another important thing is, which is same thing, the higher the concentration, okay, what am I saying? This this depletion region, we also want it to shrink. This is also, sorry. So this depletion region, this is N, this is P, this is reverse bias. So we want this thing to be strong, to be very tight. We don't want it to be loose. Now the thing is, higher the concentration of the doping, more kind of impurity doping of N, making it N, more impurity doping make it P. The higher the doping, the stronger this is, or smaller this is. Stronger means smaller. Because if it is wider, that means you can easily break it. A very tight thing, and this is something I believe, yeah, I have it here. This is one. I think this one is not correct. It should be like this. So look at there. The channel doping, higher this is, smaller is the depth. And smaller depth is good. So think of this one here. I try to create a gate here. I mean, similar to the channel. So if I apply positive here, that's the case. There are a lot of holes here. What happens? When I apply more voltage, a lot of electrons, I'm bringing electrons here. As electrons leave, they leave behind positive charge. That thing happens. Look pretty strong because a lot of carrier there. If the concentration is low, this is type of, I'm just to explain you this. So this is the kind of the depletion region, or what you can say the junction. So think like that. Now we have a little bit two opposite things here. First I said, if higher concentration, mobility is less. But higher concentration also makes the reverse bias good one. So what we do is, here for this region, we do additional implants which make this doping more P, and because of that, this reverse bias area actually here is pretty strong. And that also improves current here. It also ensures that the effect of electric field is kind of not as much as before. Okay, this is really kind of barrier there, to kind of a barrier of this heavy charging or heavy influence of electric field over here. So these were the halo things. I hope I'm clear. Again, this lower concentration here, better mobility of electrons, higher doping here, and they didn't want to have higher doping here because it will impact the mobility. Only this one here in this region to reduce the effect of this higher electric field and have a stronger barrier. All right, hopefully what I explained makes some sense, and that's it. So these were those three techniques, and even below 130 nanometer, those things you will see kept coming. That's all for today, and yeah, from tomorrow we will start going below 130 nanometer. See you. Bye.